it still might be the case that although there might be some domain expertise, it might not be sufficient to come up with a model that's good enough to use, and we might do better by taking data and actually learning the dependencies that the data tell us are the most significant. A second setting where this might happen is where we don't necessarily even care about using the network, we just want to discover the network. And this kind of use model occurs, for example, in scientific or biological data sets, for example, where the goal is to discover the interrelationship between the variables just so that we understand the domain better. So let's focus for a moment on the first of these two cases, where our goal is to learn a network for the purpose of using it. And let's think about the kinds of mistakes that might happen and how they affect the ability of the network to apply well to new instances. So let's imagine that the true network is this one over here. And now let's consider different kinds of mistakes that a learning algorithm might make. So in one case, for example, the learning algorithm might learn a network that's missing an arc. On the other hand, it might learn a network to which we've added an arc. Now, of course, one can also have cases where we have a bit of each, but let's think about these two types of errors separately. If we're missing an arc, effectively the independencies that the learned network tells us is incorrect. That is, relative to the ground truth network, which is this one, which if you remember we called it G star, the network that we learned is making independence assumptions that are not correct relative to G star. Conversely, in this case, we have spurious dependencies. That is, when we have added an arc, there is a spurious dependency in this case between A and B. Now, what are the implications of this? If we're missing an arc, then the correct distribution P star cannot be learned. That is, there is no way in general, if P star was associated with this network over here, that is, G star is a perfect map for P star, then we can't learn P star using a network that's missing an edge. Now, that might seem like a very bad idea, and we would prefer perhaps the error model on the right, which even though it has these excess edges, it does allow us to correctly learn P star. That is, this additional edge over here between A and B, there is a setting of the parameters for which the correct distribution P star can still be estimated on this network structure. So it might seem that this error mode is actually better than the one where we're missing an arc. But empirically, that actually turns out to be an oversimplified view. Specifically, the model where we have excess arcs gives rise to an increase in the number of parameters. And the more parameters we have to elicit, the harder it is to elicit them correctly given the limited amount of data. We've already talked about spurious dependencies. That is, when we have added an arc, there is a spurious dependency in this case between A and B. Now, what are the implications of this? If we're missing an arc, then the correct distribution P star cannot be learned. That is, there is no way in general, if P star was associated with this network over here, that is G star is a perfect map for P star, then we can't learn P star using a network that's missing an edge. Now, that might seem like a very bad idea, and we would prefer perhaps the error model on the right, which even though it has these excess edges, it does allow us to correctly learn P star. That is, this additional edge over here between A and B, there is a setting of the parameters for which the correct distribution P star can still be estimated on this network structure. So it might seem that this error mode is actually better than the one where we're missing an arc. But empirically, that actually turns out to be an oversimplified view. Specifically, the model where we have excess arcs gives rise to an increase in the number of parameters. And the more parameters we have to elicit, the harder it is to elicit them correctly given the limited amount of data. We've already talked about this when we talked about fragmentation as the number of the data as the number of parents increases. And so one of the important conclusions from this is that this, as we've already seen, can give rise to worse generalization, which means worse performance on unseen instances. And so the fact is that sometimes having fewer edges could actually generalize better than having more edges, even though the correct distribution cannot be encoded. And so the trade-offs between missing arcs and extra arcs are subtle, and it's not always clear which is the right, which is going to give us the best performance. So with that introduction, what is the way in which we typically learn Bayesian network structure from data? The general paradigm, which we will refine in subsequent parts of this segment of the course, is that we define a scoring function that evaluates for each structure how well that structure matches the data. So here we have a data set D, and we have, in this case, 3 example network structures, and we're going to define a scoring function that tells us for each of these network structures how good it is relative to the data that we've seen. And then we have the goal of searching for a network structure that maximizes the score. And so we have now turned the learning problem into an optimization problem. It's an optimization over a combinatorial space, the space of network structures, and by defining a score that gives us the objective that we're trying to optimize, and now we need to come up with an algorithm that optimizes that score. So we've separated this out into the score component and the optimization component, and we'll talk separately about each of these in subsequent parts. So we talked about the fact that we can view Bayesian structure learning as 2 pieces. One is defining a scoring function that allows us to evaluate different networks, and the second is as a search procedure, an optimization procedure that allows us to select among the networks the one that has the highest score. We're going to first talk about scoring functions, and initially we're going to talk about what is perhaps the simplest score that we can consider, which is the likelihood score. So we've already talked about likelihood as a way of evaluating the quality of a given network. And so here the likelihood score can be defined as the graph and the parameters that maximize the likelihood, or in this case, the log likelihood of the data. So the score, the likelihood score of a graph is the log likelihood of the graph accompanied by the parameter setting theta hat, which is the maximum likelihood estimate of the parameters given the graph G and the data D. So for any graph, we figure out what are the best possible parameters to use for that graph, and then we use that as a way of evaluating the quality of the graph that we learned. So let's look at let's look at a simple example to see what the likelihood score looks like. So here we have a distribution over 2 random variables, x and y, and let's consider 2 graphs. G0 on the left has no edge between x and y, and G1 on the right has an edge from x to y. and the y to x case would be symmetrical. So we're just going to look at these two graphs. The likelihood score of a graph, of this graph relative to D, by the decomposition of the likelihood function that we've already seen, is the sum over all instances M of the log of the parameter for the value of x in the mth data instance plus the log of the parameter for y in the for the y value in the mth data instance. So this is just the decomposition of the log likelihood that we used when we talked about parameter estimation. Conversely, when we look at G1, we have a very similar formula where again we sum over all instances, and for the x that has no parents we have log of theta hat xm, where again xm is the value of x in the mth data instance, and for the y value we have log of theta hat of ym given xm. And in both cases, theta hat are the maximum likelihood parameters in their respective graphs. So on the left it's theta hat for the graph G0, and on the right it's the maximum likelihood theta hat for the graph G1. Now let's refine this analysis a little bit more by converting it to a somewhat different notation. First, we're going to look at the difference between these two likelihood scores. So we're going to look at the score for G1 and subtract away the score for G0, and then we're going to see whether that score is positive or negative. That is, whether we prefer G1 to G0 or not. So notice that the term over here, the first term, the x term, is the same in both of these graphs, and so it cancels out, and so what we have left over is the sum over m of log of theta hat ym given xm minus log of theta hat of ym. Now, we can reformulate this by looking at the sufficient statistics. And specifically, we're going to have the term theta hat ym given xm recur every time we have a particular value y and a particular value x. So we're going to sum up over all values little x and little y, and the parameter log of theta hat y given x is going to occur m of xy times, where m of xy is the sufficient statistics or the counts for that particular configuration of events in the dataset D. The second term, the one that we're subtracting, is a sum over y of m of y log of theta hat of y, where again m of y is the sufficient statistics. Now we're going to rewrite this in terms of this distribution over here called p hat. P hat is what's called the empirical distribution. It's what happens when we look at our data set D and just look at the frequencies of different events. So m of xy is simply the number of data instances m times p hat of xy, because this is the frequency of the event and this is the total number of data instances, and so m of xy is just the product of those two. So we can write the first term as m times sum of xy p hat of xy. And interestingly, we can also rewrite the maximum likelihood estimation parameters in terms of p hat as well, because theta hat of y given x is simply the fraction of the y cases among all the x cases, which is exactly the same as p hat of y given x. Similarly, the second term turns into m times p hat times the sum over y p hat of y log of p hat of y. So that now converted all of the expressions, the m's and the thetas, into a single vocabulary, which are these empirical distributions p hat. So now let's take the m out of the equation, and furthermore, look at the sum over y as the sum over pairs xy. So we've artificially introduced a variable x into the second summation, sum over y p hat of y, and now we're going to rewrite that as sum over xy p hat of xy. And because x doesn't appear in the expression log p hat of y, we can do that because sum over x p hat of xy is equal to p hat of y. So looking at these two expressions together, we can now move around some things by utilizing properties of the logarithm and derive that this is equivalent to the following equation. This is m times the sum over xy, p hat of xy, log p hat of xy divided by p hat of x, p hat of y. And the reason why that's the case is that p hat of y given x is equal to p hat of y comma x divided by p hat of y, divided by p hat of x, and now by moving around the logarithms we get exactly this expression. Now importantly, this expression here inside the summation over here has a name, and that summation is called the mutual information and is usually denoted as I sub p hat, in this case the distribution p hat, between x and y. So why is this called mutual information? It's because it measures, if you look at this, the distance on average between the joint distribution x and y, p hat of xy in the numerator, relative to the distribution that we would get if the distribution was a product of marginals, so p hat of x times p hat of y. So you can think of this term inside the log as a relative error, if you will, a distance between the joint distribution and the product of the marginals. And now we're taking the average of the log of this expression, averaged by how frequent the different cases x, y are. And so that's, so you can think of it as an average distance between the joint distribution and the one that we would get if this was a product of marginals. So this is an information theoretic property, which, as I said, is called the mutual information. And so if we now generalize this analysis to an arbitrary network, it turns out that the p hat between x and y. So why is this called mutual information? It's because it measures, if you look at this, the distance on average between the joint distribution x and y, p hat of xy in the numerator, relative to the distribution that we would get if the distribution was a product of marginals, so p hat of x times p hat of y. So you can think of this term inside the log as a relative error, if you will, a distance between the joint distribution and the product of the marginals. And now we're taking the average of the log of this expression, averaged by how frequent the different cases x, y are. And so that's, so you can think of it as an average distance between the joint distribution and the one that we would get if this was a product of marginals. So this is an information theoretic property, which, as I said, is called the mutual information. And so if we now generalize this analysis to an arbitrary network, it turns out that the likelihood score for any graph can be viewed as can be rewritten as the number of data instances m times the sum over all variables I of the mutual information again between a node and its parents in the graph, minus a constant term that is constant relative to the graph structure. The second term is m times the sum of the entropies of the individual variables, and this term doesn't depend on g. Now, why is this a significant result? It's significant because it tells us that the value of a network, the score of the network, if we use the likelihood score, is higher. So score is higher if xi is correlated with its parents, which is a very intuitive property. The more a variable is correlated with a parent, the better the network structure, which means we would want to put as a parent of a variable a parent that is highly correlated with it, which is kind of exactly the behavior that you would intuitively hope for. So this is a good result because it tells us that the parents that we pick for a variable are the ones that have the highest correlation with it, the ones that have the highest mutual information. And that's a very satisfying result. However, as we now show, this mutual information result also has some negative consequences. So to understand that, let's go back to our simple example, and let's look at the difference between the scores of these two graphs. The graph G1 on the left that has the edge and the graph G0 on the right that doesn't. And let's look at the difference between those two scores. That difference, if it's positive, suggests that we should pick the graph G1. And if it's negative, tells us that the maximum likelihood score will pick the graph G0. And that difference is m, the number of samples, times the mutual information between the variables x and y in the empirical distribution p hat. Now, a well-known result from information theory is that the mutual information, this quantity over here, is always non-negative for any distribution p. Furthermore, this mutual information is equal to zero. That is, this inequality turns into an equality if and only if x and y are actually independent in the distribution relative to which we're computing the mutual information, which in this case is the distribution p hat. Now, even if x and y were actually independent in the original distribution, the one that generated the training instances, it is still very unlikely that we will achieve exact and perfect independence in the empirical distribution just because of statistical fluctuations in the set of samples that are generated. And so, even if x and y are independent, it is almost never the case that they are independent in p hat, which means that in almost all cases, this mutual information between x and y is going to be greater than zero, almost always. Which tells us that adding this edge can never hurt and almost always helps, and that's true not just in this simple example, but in other cases as well. That is, it almost always is better in terms of the likelihood score to have more edges rather than fewer edges. That will always increase the likelihood score. Which means that in general, except for very unusual circumstances, the likelihood score will be maximized for the fully connected network. So that gives rise to a very significant overfitting effect, because as we've already seen, the more edges we have, the more difficult it is to fit the parameters, because we have fragmentation of our data set into these tiny little buckets, each of which has a very small number of instances in it. So how do we avoid overfitting? It turns out that there are several different strategies that are typically employed. The first is to restrict the hypothesis space to basically prevent the algorithm from overfitting. And we can do that by restricting the number of parents that we allow per node, or some kind of restriction on the number of parameters. This is usually easier to enforce, and so that's a more common strategy. A second, more flexible strategy is to use a scoring function that makes a better set of trade-offs. That is, where there is a penalty on the complexity of the model at the same time that we're trying to get a good fit to the training data. And that's a more flexible strategy than a hard constraint on the model complexity, because if there is a very strong signal for some correlation between a pair of variables, that can eventually outweigh the complexity penalty and allow that edge to be added in, whereas if we have a hard constraint, we might never be able to learn a model that is the appropriate one, simply because it's never going to be it's not going to fit into the restricted hypothesis space. These complexity penalizing scores generally fall into two categories. There's ones that explicitly penalize complexity, and then there's a class of models called the Bayesian, a class of scores called the Bayesian scores, which, as we'll see, average over all possible parameter values following the Bayesian paradigm that says that anything we have uncertainty over, we should have a distribution over. And as we'll see, that gives rise naturally to a score that avoids overfitting. To summarize, The likelihood score is a score that evaluates a model G by looking at the log likelihood of the data relative to G using the MLE parameters for G. And that set of parameters was optimized to maximize the likelihood of D, and therefore is very well geared to trying to capture the exact characteristics of the data for better and for worse. So for better, it gives us a very nice information theoretic interpretation of the set of edges that are chosen, the set of parents that are chosen for a given variable in terms of the dependencies that, that we encode in the graph G. Conversely, that same characterization also shows us that we're guaranteed to overfit the model to the training data unless we somehow impose constraints or otherwise penalize model complexity. We talked about BaseNet structure learning as the task of optimizing a score over a space of network structures. And one of the big design choices that we have to make in this context is which scoring function to use. Our first attempt at that was to use the likelihood score, but as we've already seen, the likelihood score is very susceptible to overfitting and will invariably learn the most complicated network that it can given the constraints that we impose on our space. We now consider a different approach in which, rather than constraining the space, or maybe in addition to constraining the space, we're also going to impose a penalty on the complexity of the structure that we learn so as to force the model to force the learning algorithm to trade off model complexity with the fit to the data. And specifically, the model, specifically the score that we're going to look at right now is something called the BIC score. So let's look at one way of penalizing complexity, which is the one that the BIC score uses. The BIC score has two terms in it. The first is just the likelihood of the graph and its maximum likelihood parameters relative to the data. This is a familiar term. This is the term that represents the same thing as the likelihood score. So this term is just score L of G relative to D, and were we to use this in isolation, we would get the same overfitting behavior. But we add to this a penalty term. This is the second term here on the right, and that term subtracts log of M over 2 times the dimension of G. So let's understand what these different pieces are. M is the number of training instances, and the dimension of G is the number of independent parameters in the network. So we talked about the concept of independent parameters in the context of multinomial networks. And as a reminder, a multinomial distribution has one fewer independent parameters than the number of entries in the multinomial. And from that, we can compute the number of independent parameters for any multinomial network. So this basically counts the number of degrees of freedom that we have in the network in terms of estimating independent parameters in it. And so these two terms balance each other out. We've already seen that the term on the left, the log likelihood, tries to push towards a better fit to the training data, whereas the term on the right, the penalty term, is going to try and keep the number of independent parameters and therefore the network complexity down. And so this score provides us with some kind of trade-off between fit to data and model complexity. Now, this is one choice in terms of this trade-off, and in fact, there are other scores that use a different trade-off between those two terms, but this one is one that's very commonly used in practice and has several distinct motivations, some of which we'll talk about, and others not. One comment that's worth making, though, is that the negation of this score, so if we negate this entire term, that is often called the MDL criterion, where MDL stands for minimum description length. And so, in fact, this notion of minimum description length is an information theoretic justification for this. And the other justification for this is one that's derived from a more Bayesian criterion, which is why BIC actually stands for Bayesian information criterion. Let's look at the asymptotic behavior of this penalized score. We've already seen that in the context of the likelihood score, it really doesn't matter how much training data we have. We will almost always pick the most densely connected network that our assumptions allow. But this is no longer the case when we have this penalized score. So to understand that, let's break down the first of these two terms, which is the likelihood score, and remind ourselves that at least in the context of multinomial networks, the likelihood score can be rewritten as in the following way. So this is the breakdown of the likelihood score, and it has these two terms. The first is the number of data instances m times the sum over the variables xi of the mutual information between xi and its parents in the network. And that mutual information is relative to the empirical distribution p hat. The second term in the likelihood score is a term which is also m times the sum over the variables of the entropy of the variable, again in the empirical distribution. And as we've already discussed before, this term is independent of g, and so doesn't affect the choice of which structure is selected because it's the same for all structures. And so we have these two terms that are playing off against each other. We have the term over here, the red term, which is m times the sum of the mutual informations. And we have the second term, the blue term, which is the log of m over 2 times the number of independent parameters in G. Now, if we consider these two terms, we see that the mutual information term grows linearly with m, whereas the complexity term grows logarithmically with m. And so as we get more and more data instances, we put more emphasis on the fit to data and less emphasis on the model complexity. So intuitively, we would infer that we would, as we have more data instances, we'd be more amenable to learning more complicated structures. So that property gives rise to a very important result that we can state regarding the BIC score, and that is a result called consistency. Consistency tells us what behavior we would get, what network we would learn as the number of samples grows to infinity. And so here we're going to assume that the data is actually generated from a particular true structure G star. So there is a G star, because otherwise the result doesn't really make, can't really be stated. And what the consistency property says is that as m grows to infinity, the true structure G star max is going to be the one that maximizes the score. Now that by itself is not quite right, as we can see, because the true structure G star might have several other structures that are I equivalent to it, and we've already seen that the likelihood score, and in fact it also turns out to be the case that the penalty term are the same for I equivalent networks. And so it's not just the true structure alone that will maximize the score, it's the true structure or any other structure which is I equivalent to it. But as far as we're concerned, that's fine, because we've effectively learned the correct representation of the probability distribution. So to understand why this result is true, we're going to give just a very high-level intuitive argument. We're not going to prove the theorem. It's a little bit tricky to prove completely formally. So let's first consider the case of why this is not going to overfit. That is why we're not going to have spurious edges learned in maximizing the score as the number of instances grows to infinity. So here we go back and look at this formula over here, and we see that as m grows to infinity, p hat is going to approach p star, where p star is my true underlying distribution. And so what we're going to have in this first term over here is effectively the mutual information relative to p star between xi and its parents. And in that p star, the mutual information between xi and its parents is you don't get any benefit from adding additional parents, spurious parents. That is, the mutual information in P star for a spurious parent is not going to grow, because in the true underlying distribution P star, there is no additional independence. There's no additional correlation that we have. And so at that point, we're going to have that the more complicated structure is about the same as G star in terms of this first term, but the spurious edges are going to cost us in terms of the number of parameters in the blue term, and so these spurious edges will not contribute to the data likelihood term, but will be penalized more, and so we will choose the sparser network that corresponds to G star. Conversely, why do we not underfit? That is, why do we eventually learn all correct edges? And that is because the data likelihood term tells us that edges that are required, that is, edges that are in G star, for example, or in the I equivalent network, will, if we don't have them there, this mutual information term will be lower than it could be. And so we will have a higher score by including those terms in the model. And because this mutual information term grows with m linearly versus the penalty term, which grows logarithmically, then eventually the first term will dominate, and we will have and it will be beneficial for the learning algorithm to add that edge, the required edge in G star. So this is a high-level, very hand-wavy argument, but at least it gives an intuition as to why consistency holds. So to summarize, the BIC score is a very simple score that trades off model complexity with the fit to data, and therefore has the important property of asymptotic consistency, which means that if the data were actually generated by a network G star, which is a perfect map for the distribution, then either G star or networks I equivalent to it will have the highest score as m grows to infinity. We talked about Bayes-net structure learning as the problem of optimizing a scoring function over the space of network structures, and we also talked about how the likelihood score, which is the simplest score that one could come up with, has significant issues relative to overfitting. We're now going to look at a different score that's derived from Bayesian principles, and we're going to see how that score, although it has some surface similarity to the likelihood score, is a considerably better score in terms of its avoiding of overfitting. So the Bayesian score is derived from the Bayesian paradigm that says that anything that we have uncertainty over needs to have a probability distribution over it. And so if we have uncertainty over graphs, then we need to have a prior over graphs. And if we have uncertainty over parameters, we need to have uncertainty over parameters, a probability distribution. And so if we now define our optimization problem as that of finding the graph G that maximizes the probability of G given D. Now, if we rewrite the probability of G given D using Bayes' rule, we end up with the following expression, P of D given G times P of G divided by P of D. So let's look at each of those terms separately. The first of these is a term called the marginal likelihood. P of D given G is the probability of the data given the graph. The second of these terms, P of G, is a prior over graph structures. And the final term, P of D, the denominator, is called the marginal probability of the data. Now, importantly, this marginal probability of the data is independent of G, and so is not going to affect the choice of which graph we select, and therefore we can ignore it in the context of a model selection problem, that is, of finding the single graph or a graph that maximizes the score. And so we're going to define the Bayesian score, score B, of G relative to a data set D, as the log of the numerator of this expression. So the log of the marginal likelihood plus the log of the prior over graphs. Now we might think that this score is going to avoid overfitting because of its the use of the prior over graphs. And although that prior can play a role, actually it turns out to be a significantly less important role than the first of these terms, which is the marginal likelihood. So let's look at the marginal likelihood in a little bit more depth. So the marginal likelihood, P of D given G, is not, as it happens, the same as the log likelihood, because that marginal likelihood is something that integrates over all possible settings of the parameters. And so from a mathematical perspective, what we're going to do is we're going to introduce a variable theta G into the probability expression, and then we're going to integrate it out, which is the same as summing it out, only it's a continuous space, so we're going to use integrals. So P of D given G is the integral over all possible model parameterizations theta G of the probability of D given G and theta G times the probability of theta G given G. Now, the first of these two terms is the likelihood, which is exactly the component that we used in the log likelihood score. But importantly, unlike the likelihood score, we're not computing P of D given G and theta G just for the maximum likelihood parameters theta hat G. Rather, we're computing this probability averaged out over all possible parameter settings, which gives us a considerably less optimistic assessment of the probability of the data given a particular structure, because we have to take into consideration not just a single parameter setting that is geared exactly to our data set, which is this theta hat set of parameters, but rather averaging out over all possible parameter settings theta G using the prior over parameters. So that less optimistic assessment is sort of one intuition as to why this might not overfit as much. But it turns out there is another, perhaps even more intuitive explanation as to why this score reduces overfitting. So let's look at this marginal likelihood term, P of D given G, and just rewrite it as the probability of all of the instances, x1 up to xm, given G. And what we're going to do is we're going to now break up this joint distribution using the chain rule for probabilities, not the chain rule for Bayesian networks, just the chain rule for probabilities. And we can write that as the probability of x1 given G times the probability of x2 given x1 and G times the probability of x3 given x1 and x2 times blah, blah, blah up to the probability of xm given all of the previous ones, x1 up to xm minus 1 and G. And if we look at each of these terms, each of these is effectively making a prediction over an unseen instance, say xm, given x1 up to xm minus 1. So you can think of it as almost doing some kind of cross-validation or generalization or estimate of generalization ability, because we're estimating the ability to predict an unseen instance given the previous ones. And so the probability of D, in some sense, incorporates into it some kind of analysis of generalization ability. Now, you might say, well, surely the likelihood does, the standard likelihood score does exactly the same thing. But a little bit more thought reveals that if we want to do this kind of analysis for the maximum likelihood set of parameters, that maximum likelihood set of parameters, theta hat G, depends on all of D, all of the instances D, in D. And so we can't break it down in this way because if we had theta hat G on the right-hand side, it's already incorporating into it all of the instances, including the unseen ones, which is yet another intuition as to why that the maximum likelihood score tends to overfit. Now, the Bayesian score might look a little bit scary because it has all this integral in it, and who knows how we would ever compute it. It turns out that for the case of multinomial Bayesian networks, the likelihood, the Bayesian score can actually be written in closed form using a function called the gamma function. The gamma function is as written over here. It's also an integral, but it turns out that the gamma function is really just a continuous extension of the factorial function, because gamma x satisfies the equality gamma x is equal to x times gamma x minus 1. And most computers have an implementation of the gamma function in them. So with the gamma function, we can actually rewrite the probability of D given G as a product that looks as follows. The first is, first we have a product over all variables I, and then we have two different products included in this big outer product. The first is a product over the parent set ui of multiplying over all possible values of the parent set. And here we have an expression involving gamma functions, where this expression involves both the Dirichlet prior parameters, the alphas, as well as the sufficient statistics. So the first product enumerates over all possible assignments to the parents. And then we have an inner product, yet another inner product, which enumerates over all possible values of the variable itself. The variable, all possible values xij of the variable xi. And once again, we have gamma terms that involve both the prior as well as the sufficient statistics. And while this expression might look still a little bit scary, it's something that one can just plug into the computer and compute quite easily. Another valuable property of this marginal likelihood, if we look at it a little bit more, and now we also take its logarithm, is we see that this expression which was originally a product over variables I of some complicated expression relating to xi, is actually something that, if we take the log, turns into a sum over I of the family score, of something that can be viewed as the family score for a variable xi and its parent set together. And so just like other scores that we've seen before, the scoring function can decomposes as a sum over I of terms involving only xi and its parents. And we'll see that this property can be quite important from a computational perspective. How do we, so now building up from the marginal likelihood, the second term in this expression is log of P of G. And so in order to accommodate for that, we need to have a prior over P of G. And there's a variety of different priors that people have used. It turns out that a quite common choice is to simply make P of G constant. And that although that doesn't impose explicitly any penalty on complexity, it turns out that it works quite well because of the penalty imposed on complexity by the marginal likelihood. But if we want to build in additional penalties on complexity, we can make the prior be something that exponentially penalizes the number of edges or penalizes the number of parameters, and that induces additional sparsity. Now, importantly, we don't actually want to define a prior probability over graph structures and make sure that it correctly normalizes over all possible structures and even more so over all possible acyclic structures. But fortunately, we don't have to, because the normalizing constant in this distribution P of G is the constant across different networks and can therefore be ignored completely, and we only need to consider the term that changes with the graph structure and ignore the normalizing constant or partition function. That's the structure prior. What about the parameter prior? The parameter prior that we use in the context of the Bayesian score, the one that's most commonly used, is something called the BDE prior. And the BDE prior is something that we've actually seen before when we were talking about parameter estimation for Bayesian networks. And as a reminder, the BDE prior is defined by two components. One is an equivalent sample size alpha, which is the total number of instances that we might have seen in some imaginary universe. And the second is a probability distribution P0, typically encoded by a prior Bayesian network B0, which encodes sort of our prior beliefs about the universe. And so we define now the imaginary counts that we might have seen for a particular combination of values for little xi and a particular assignments for its parents to be alpha, which is the total number of counts that we've seen, times the probability of that particular event xi, comma pai of g in the network, in the prior network B0. Now, an important note is that the parents of the variable xi in the graph G is not the same as the parents of xi in the prior network B0. In fact, in many cases, we choose the network B0 to be one that has no edges, where all variables are independent. But we compute the probability distribution in B0 and then use that to compute the hyperparameters alpha that are used in the context of the learning problem for a given graph G. And the important thing is now that the single network B0 provides us with priors for all of the candidate networks. So we don't need to elicit priors for exponentially many networks. We have a single network B0 in a single equivalent sample size, and we can use that to compute the parameter prior P of theta given G over all possible networks that we're interested in evaluating. Now, other than its convenience, why this prior as opposed to others, it turns out that one can show that this prior is the unique prior over multinomial Bayesian networks, with the important property that if two networks are I-equivalent, then they have the same Bayesian score. That is, if we used a different set of Dirichlet priors other than one that fits this mold, we would have a situation where you might have two networks G and G prime that were I-equivalent that have different Bayesian scores, and there's really no justification for that in terms of incorporating that into the parameter priors, because these networks are completely equivalent in their ability to represent the probability distribution, or the same set of probability distributions, so why would we have one of them have a different Bayesian score than others? Or rather, if we do have some prior knowledge that one of these graphs is more suitable than the other, we should put that into our structure prior, not into our parameter prior. One interesting property of the BDE score has to do with its asymptotic behavior. So let's consider what happens to the BDE score as, or in fact a Bayesian score in general, as m goes to infinity. And it turns out that as m goes to infinity, a network G with Dirichlet priors satisfies the following in terms of the marginal likelihood. That the log of the marginal likelihood is equal to the sum of these three terms. The first of these is just the log likelihood of the data given the maximum likelihood parameters theta hat G. So this is just a likelihood score, which we've already seen has some good properties in terms of trying to fit the data, but on the other hand is also liable to overfit. The second term, however, is log of m over 2, where m is the number of instances, times dim G, which is the number of independent parameters. which, as we've seen in the context of a multinomial distribution, is the number of entries in the distribution minus 1. And this term has a negative sign, which means that we are going, the log of the marginal likelihood is going to be decreased as we increase the number of parameters. And so there is a tension between those two terms. The first of these tries to have more complicated networks in order to maximize the fit to data, as we've already seen. And the second tries to reduce the complexity of the model by decreasing the number of parameters. The third term is this term O of 1, which indicates in a formal notation that this third term is effectively constant relative to m, which means it doesn't grow with m, with the number of instances. Which means that as the number of instances grows, only these first two terms are going to play a role in terms of evaluating which structure is going to be selected. Now, these first two terms, as it happens, have a name, and that name is something called the BIC score, which really looks just at the likelihood component and the penalty term. And in a different part of this course, we talk about the BIC score and some of the properties that it has, specifically, for example, the fact that as m grows to infinity, the score is consistent, which means that the graph or one of its if the correct graph for one of its I-equivalent graphs is going to have the highest score among all possible graphs that we're considering. So this is yet another demonstration that the Bayesian score is a way of avoiding overfitting, because at the large sample limit we will learn a correct graph, either the correct graph for one of its I-equivalent structures. To summarize, the Bayesian score uses Bayesian principles, specifically averaging out over parameters that we have uncertainty over to avoid overfitting. The Bayesian score is most often instantiated as a particular variant called BDE, which requires that we assess a prior network in order to compute the prior over parameters, but that also allows us to a natural place to incorporate prior knowledge into the learning algorithm. And the BDE prior has the important property that I-equivalent networks have the same score. The Bayesian score is at the large sample limit equivalent to a different score called BIC, which we analyze separately in this course. And as a consequence of this equivalence, one can show that it's asymptotically consistent in that it learns the correct network as m goes to infinity. Now, while this asymptotic behavior is an important one, it's also important to realize that we don't often have a very, very large number of samples, or at least not in a large number of applications. And so it's important to consider also the behavior for a more reasonable number of samples m. And in this case, it can be shown that the BIC score tends to underfit the tends to underfit the model structure, in the sense that it'll learn models that are too sparse. Having defined a set of structure scoring criteria, we now turn to the problem of trying to optimize that structure score over a set of possible candidate structures. And we're first going to consider the specific case of trees. So just as a reminder, we defined a scoring function that evaluates how well a structure matches the data. So here is a set of different structures, and here is a graphical depiction of our score, and we would like to search for a structure that maximizes the score. So this is an optimization problem where the input is a training set, a scoring function, and a set of possible structures, and the output is a network. And it turns out that absolutely the key property for computational efficiency is decomposability of the score, which is the decomposition of a score as a sum of family scores, which we've seen before. So the first problem that we're going to focus on is that of learning either a tree or a forest. So what is a forest? A forest is at most one parent per variable. So here, for example, is one forest. And notice that a forest doesn't have to be connected. That is, it can be separate, disconnected components. A tree, on the other hand, would require that the graph be connected, so we might have this edge, for example, as well. And notice that it's still a directed tree. So why should we care about learning trees, given the trees are so degenerate? They're so restricted in their expressive power. Well, there's different types of reasons why we like trees. First of all, it turns out that the math is very elegant. Now, that might not be a convincing reason, but that elegant math gives rise to what turns out to be a very efficient optimization over the set of trees that allows me to solve it extremely effectively, even for very high-dimensional problems. And then finally, the third reason is that trees are limited expressive power, but that also implies that their parameterization is very sparse. And because their parameterization is sparse, it means they're less susceptible to overfitting. And therefore, at least in cases where M is small relative to the network complexity, relative to N, then it turns out that it can provide better generalization, even though it doesn't capture the full expressive power that we would hope to have in our network. So let's now talk about the problem of learning forests, and we're going to define a little bit of notation. We're going to define P of I for variable I to be the parent of xi, or 0 in case xi has no parent. So note that each variable has at most one parent, so this works. So now let's look at our decomposable score, and again, this can be any of the three scores that we talked about because they all have this property. So the score is a sum of score of individual families xi and their parents. And now the parents are very simple because we have only at most one parent per variable, and so we're going to divide this into two cases. The first case is nodes that have a parent, and the second one is nodes that don't. And so for the nodes that have a parent, what we have is the score of xi given its one parent. And for the nodes that don't have a parent, it's just the score of xi as a standalone variable. And now we're going to shuffle things around a little bit, and we're going to do the following. We're going to introduce into this expression a score of xi, and then we're going to add it back in over here. So now we have a sum over all variables. So notice this is I equals 1 to n of a score of xi in isolation. But for the xi's that have a parent, I've subtracted that off in the first summation. And so I've compensated for it on both sides. The important property of this expression is that this is the same for all trees. And so it doesn't affect the comparison between one tree and the other. And so the only expression that I need to consider when comparing two trees is this expression over here, which is the sum over I of the score of xi with its parent minus the score of xi without its parent. So you can think of this as the score of the empty network, and the first expression, the first summation, is the improvement that a tree gives me over the empty network. And so the score now turns into a sum of edge scores, where each of these is a score of an edge from pi to I, plus a constant that doesn't affect the selection of the networks. And that turns out to be the critical piece for doing the optimization efficiently. So let's see how this all works out. So first of all, we can define the weight of an edge from I to j to be the score of xj with its parent xi minus the score of xj. This is exactly the term that we saw on the previous slide in the first of the two summations. Now, for the likelihood score, if we go back and plug in the likelihood score, we can see that this weight turns out to be m times the mutual information between I and j. So the extent to which they're correlated with each other. And because mutual information is always non-negative, it means that all edge weights are always non-negative. And that means that the optimal structure is always a tree. That is, there's always benefit, or at least there's no penalty for including additional edges. For BIC or BDE, we know that there is a penalty score. So even if introducing an edge from xj to xi increases the likelihood, we might end up paying for it more in the penalty score than what we gained. And so the weights, this weight, can actually be negative. At which point the optimal structure might actually be a forest. That is, it might be detrimental to our overall score to make the graph fully connected. Not fully connected, to make the graph connected. That is, a tree rather than a forest. Okay. Now a second observation. A score, remember, satisfies score equivalence. This is a property that we defined before, if I equivalent structures have the same score. And all of the scores that we talked about are score equivalent. It turns out that for a score equivalent score, we can show that the weight from I to j is equal to the weight from j to I. That is, we can compute this expression over here for j to I or for I to j, and we're going to get the exact same value. And you can see that in the likelihood score directly because mutual information doesn't have any kind of directionality associated with it. Mutual information of xi to xj is the same as mutual information from xj to xi. So for likelihood score, you could just see that. And it turns out that for the other cases, it also follows. And so that means that we can define an undirected graph where it doesn't really matter whether I go from I to j or from j to I. And because the weight is the same for both. And so for score equivalent scores, we therefore get the following algorithm. We can define an undirected graph with nodes being the variables in my graphical model. And then I define a weight, wij, to be the max of the score xi between xi and xj and 0. And remember that it doesn't matter whether I do ij or ji here, we're going to get the exact same thing for score equivalent networks. The 0 is going to be a way of eliminating negative edges so that I can optimize things efficiently without having to worry about negative edge costs.
I can go ahead and find a forest or a tree that has the maximal weight. And the nice thing is it turns out that you could use any of the standard algorithms for maximum weight spanning trees in order to do this. So for example, either Prim's or Kruskal's algorithm can be used to solve this, and we can in fact find the solution in time that is O of n squared, which is an inevitable cost given them considering all n squared combinations in terms of pairs of edges. And then if I end up having edges of weight 0, that indicates that the edge there potentially was derived from a negative component of the score. So I remove all of the edges whose weight is 0 to produce a forest. And that is an O of n squared time algorithm for finding the absolutely optimal tree relative to any of these 3 score equivalent scores that we've defined. So let's look at an example. This is the ICU alarm network again. This is a picture of the original network. And if we apply this tree learning algorithm, we end up with the following structure, where the edges that have been marked in red are edges that existed in the original network, and the blue ones are edges that are spurious, that is, they weren't in the original network. So this blue one over here, for example, isn't in the original network. And so we see that although most even of the edges that we end up with are edges in the original network, some aren't. Some are derived from correlations that went through indirect paths in the original network. And the other thing that's important to see looking at this is that the inferred edges in the tree are intrinsically undirected. It doesn't mean that I can't force a direction on them, but the direction isn't determined by my optimization algorithm, and that means that I'm not able to determine what came before what in the original graph when I'm learning a tree. So to summarize, structure learning is an optimization problem over the combinatorial space of graphs. The decomposability property allows me to break that up as a sum of terms for different families. And that allows me to optimize in the specific case of tree structured networks using standard maximum weight spanning tree algorithms very efficiently in quadratic time.
We previously described the problem of Bayes-Net structure learning as an optimization problem, where we separated the problem into 2 pieces. One is defining a scoring function, and the second is coming up with an algorithm that optimizes that scoring function. We talked about how the optimization problem can be solved in the case where we're trying to learn a network structured as a tree, or rather a forest, where each variable has at most one parent. But what about the more general case, where we are trying to learn an unrestricted network, or perhaps one that has weaker restrictions than simply a tree? So how do we address that problem? So first, as a reminder, our input is a training set, a scoring function, and some set of possible network structures. And the output, the desired output, is some kind of network structure that maximizes the score within the set of structures that we're willing to consider. So what happens if we try to solve this optimization problem in the case where the restricted network structure is not the class of trees? Well, in the context of trees, we could apply a simple greedy algorithm for finding the maximum weight spanning tree. But when we have a more general network, even ones where we allow at most 2 parents per node, this greedy algorithm that builds up a tree no longer works. It's no longer guaranteed to find the optimal scoring network. Now, in fact, it turns out to be not surprising that that a simple algorithm is not going to work because of the following theorem. This theorem states that the problem of finding the best network, the one that has the highest score, with at most k parents, is an NP-hard problem for any k bigger than 1. So for k equal to 1, we're back in the context of trees or forests, and we have the polynomial time algorithm. But even for k equals 2, the problem turns out to be NP-hard. And so no efficient algorithm is likely to be found for this problem. So what do we do? It turns out that the standard solution is some kind of heuristic hill climbing search. So we have a current network, which is the one that we're trying to improve, and we'll talk later about where we start this process. And now we look at different changes that we could make to this network. So we can consider, for example, making local perturbations that may or may not improve the quality of the network relative to the score. What we see here, this bar represents the score. So for example, this transition adds an edge from B to D. And we can see that here that turned out to improve the score because this bar, as we see, is larger than this bar. We can consider other changes. For example, this transition removes the edge from B to C and also gives rise to a slight improvement in the score, but not as large as the one where we added the edge from B to D. On the other hand, reversing the edge from B to C, which is this transition, gives rise to a decrease in the score. And so we can look around us and see which changes to the network improve the score and which ones don't, and then probably try and go in a direction that generally improves the score. There are two main design choices that one needs to decide on when doing a heuristic search algorithm. The first is the set of operators. That is, the set of steps that we can take in perturbing one network to the other. So, for example, in the example that we just saw, we were taking local steps. We were adding edges, deleting edges, or reversing edges. And these are fairly small perturbations to the network. There's also algorithms that use much larger global steps, where we take an entire node out of the network and stick it in somewhere else. And that's a larger step that is more costly, but also takes larger moves in the space of networks. So this is one set of design choices. The second set of design choices is which search technique we end up using. So do we do what's called greedy hill climbing, where we're just trying to climb up as quickly as we can? Or do we adopt a different type of local combinatorial search algorithm, of which there are many different kinds, some of which are listed here, and there's many others, and we're not going to talk about those very much. So let's start by talking about greedy hill climbing, which is the basis for most of the Bayes net learning algorithms that are in use today. So how does greedy hill climbing work? We start with a given network initially. Often this is just the empty network, and the reason for starting with the empty network is that it induces sparsity. We don't have too complicated a network and one that's likely to overfit. We could also start with a best tree, which we get from one of the efficient tree learning algorithms that we talked about. We could also start with a random network. This is a way of exploring the space more broadly. Instead of starting out from a fixed starting point, we can start from multiple random starting points. Or in cases where we have an expert that has some knowledge of the domain, we might use prior knowledge in order to initialize the process. Having initialized, we now iteratively try and improve the network. So we consider the different steps that we can take based on the operators that we defined as being legitimate. And then for each of them, we consider the score that we obtain from all possible changes. And then we apply the change that most improves the score. So this is the greedy component. That is, we look at all possible changes and we greedily pick the one that improves the score. That gives us a new network, which we can now again update by again considering possible next step changes that we could apply to this new network. And this process continues until we get stuck. That is, when none of the modifications that we have at our disposal improves the score. And when that happens, we are at what's called a local maximum. That is a place in the space of network where no change gives rise to an improvement in the score. What are some of the pitfalls of this greedy hill climbing process? Well, the first is that this local maximum is potentially a local maximum. That is one that is not the global maximum. So if we pictorially draw the space of possible networks, we're going to draw it as continuous even though it's discrete. What we have is sort of a space that looks like this. And if we start out from a point over here and we just take small hill climbing steps, we might end up at a position that is a very poor local maximum compared to the global maximum, which could be considerably better. And this is quite common in the kind of combinatorial search that we use in this type of situation. A second problem is what's called a plateau. A plateau, if we go back to this kind of visualization that we have here, is a case where looking around us, there's a whole bunch of networks that are all effectively the same score. And while some of the directions might give rise to eventually, after a certain number of steps, to a hill, others might not. And the problem is that we don't know which direction to go because they all look exactly the same in terms of the score. This happens quite often in the case of Bayesian network structure learning, because whenever you have a network, for example, like this, other networks that are equivalent to them, for example, the one where we just reverse this edge and we have a parent that has two children as opposed to a chain, this network is equivalent to this one, I equivalent, and therefore it's going to have the same score. And in general, you're going to have a lot of neighbors when you have more complicated graphs, a lot of networks that are equivalent and therefore have the same score, and moving around between them, it's not clear which of those is going to eventually give rise to a move that breaks us out of the plateau into a network that actually has a higher score. So these are significant issues in terms of using greedy hill climbing search for optimizing the score. The issue of local maximum plateau also relates to the question of search operators that we used. And we talked about edge addition, edge deletion, and edge reversal. And the question of that one might ask is, why on earth would we need edge reversal? Because after all, edge reversal can be subsumed by an edge deletion and then an edge addition. So why do we need to add a whole new set of operators into the pool that we have to evaluate? So this, it turns out, has to do with the greedy nature of our search. So to understand that, let's look at this example. Let's assume that this is our graph G star that generated the data. And now let's assume that we're going to try and learn a network from the distribution derived from this graph. And so here we have initially our empty network, which we're going to start out with. And we have two strong correlations in this network, the one from between A and C and the one between B and C. And let's say that we picked the one between B and C as being stronger and therefore we're going to add it first. But now there's complete symmetry between the edge that might go from C to B and the edge that might go from B to C. these two networks are equivalent and they're going to have the same score. And so we can arbitrarily choose the edge that goes from C to B because it's as good as the other one. Now that that edge is in, we might go ahead and add the other one. Say we're going to add the edge from A to C. And the question is, now what? The edge from C to B is wrong, and really we'd like to reverse it. But if we don't have an edge reversal operation, the only way to do that would be to remove that edge and then add in the edge in the other direction. But removing that edge is going to cost us a lot in terms of score because this was a really good edge. In fact, it was the first one that we added. So removing it is going to cause a hit in terms of the score, and it's going to be a suboptimal move. It's not going to be a greedy move. And so if we don't have an edge reversal operation, this red network, the one that has the edge from A to C and the edge from C to B, is now going to be a local maximum. And we're not going to be able to break out of it by looking just greedily within one step unless we have an edge reversal step. So edge reversal is a way of avoiding these very common local maxima. But it doesn't address all local maxima, specifically not the bigger ones that we've also discussed. So what is the algorithm people typically use for addressing this problem without falling into this local maxima that frequently? So it turns out that a pretty good simple algorithm is the following. We do use greedy hill climbing, but we augment it with two strategies that are attempts at avoiding local maxima and plateau. The first is what's called random restarts, which is if you're climbing up and you get stuck, you take a certain number of random steps and then start climbing again. And the hope is that if we're at a local maximum that's fairly shallow, then the small number of random steps will move us into the attraction area of a better maximum, and we will continue to climb to a better optimum. A second strategy, which is useful for both local maxima and plateaus, is what's called a taboo list. A taboo list is a way of avoiding treading the same ground over and over again. So here we have a set of steps that we have taken, for example, adding an edge from A to B, or deleting an edge from C to B. And these are the steps that we've recently taken. We keep a list of the case steps that we've recently taken, and we constrain our search so that it cannot reverse any of these steps. So specifically, if add A to B is on our list, then on our taboo list, we have that delete the edge from A to B is not something that we can do while the add step is still in the list of the K most recent steps. And that forces us to make forward progress rather than doing the same step, reversing it, trying a different version of it, reversing that. And that turns out to be helpful both in avoiding local maxima as well as making some progress in the context of plateaus. So how well does this work in practice? Let's first look at a synthetic example. This is the ICU alarm network that we've seen before in the context of BaseNet parameter estimation. And what we see here are two learning scenarios. One in the blue line down here is learning parameters only with the true structure given. And the green line is where we're trying to do both parameters and structure at the same time. So trying to learn both. And we can see on the x-axis the number of data instances m, and on the y-axis the distance between the distance measured as KL divergence or relative entropy between the learned network and the true network. And what we can see here is that it's certainly the case that when we're trying to learn only parameters, we do better, at least initially. That is, for small numbers of samples, the case where we have the true network performs better in terms of learning a distribution that's close to the right one. But as we get more and more data, even with as few as around 2,000 samples were actually pretty close in performance. Now, this is very promising because it says that the structure learning problem is not intrinsically that much more difficult than that of parameter estimation alone. Now, this result, however, should be taken with a grain of salt because the problem of learning from synthetic data, which is what we have here, this is data that is generated from the network, is actually easier than the problem of learning from a real data set, because synthetic data has a much clearer and stronger signal about the correlation structure than real data, and so the performance here is probably a little bit misleading in terms of our ability to learn the network structure correctly when we don't have when the data is not quite as nice as synthetically generated data. However, there's a lot of applications where even with real data, Bayes-net structure learning has given significant advantages. One of those is this application for Microsoft Research, which aims to to predict where traffic jams are going to take place, as well as where we might have surprises in terms of having less traffic or more traffic than normal. So here the idea is that we have some number of sensors on certain major freeways, and we know, for example, that certain areas of the freeway have a lot of traffic, other areas have less traffic, and we're trying to use that data to predict parts of the road system that don't have these sensors observed in them, as well as to predict how the traffic would look in 30 or 60 minutes. So in particular, we'd like to predict, for example, parts of the road where there's going to be more traffic than we expect, so predicting a surprise, as well as a good surprise, such as less traffic than we expect. So this is a use scenario where there is some amount of prior knowledge, but it turns out that expert knowledge is not really adequate for understanding how different sources of information, different pieces of the road system, are intertwined with each other. And much better performance was derived by learning a Bayesian network structure from data that shows how these different accident reports, the hour of the day, and different areas in the freeway system are related to each other. And we can see that some of the correlations that were learned might not be quite as obvious as a human might have inferred. So, for example, the influences on this traffic in location 15, the most significant factors are the ones marked here in 4, 11, and 17, and you might not have necessarily predicted that something that's all the way across the bridge in Seattle is the most indicative factor on this particular prediction problem. And so much better performance was derived by applying learning techniques to this problem. A very different application of structure learning is in the context of this application, which aims to do scientific discovery. In this context, a data set was acquired that measures for different proteins in a cell the level of those proteins. And this was done at the level of single cells, so there were tens of thousands of measurements, each one corresponding to a protein profile in an individual cell. Now, the goal from this experiment was to discover the control mechanism of how the level of one protein can influence the level of another. So to learn, for example, that a change in the protein level of a protein such as PKC can influence the level of the protein called pKa and the level of a protein called RAF as part of the regulatory network of the cell. So this data set was acquired, and Bayesian network learning was applied to this problem in order to try and understand this regulatory network within the cell. And what we see here are the edges that were learned by the Bayes-net learning algorithm. And we can see that many of the edges, specifically all of the ones that are marked in blue, were ones that were known in the literature before. Now, while that might seem perhaps less interesting to rediscover something that was already known, this is an important validation for the Bayes-net learning algorithm because it shows us that the network is learning something valuable and correct. And furthermore, it shows that in a single experiment, Bayesian network learning applied to the right kind of data can reconstruct a cellular network that took biologists many, many years to put together. Now, not all of this is right. So, for example, this pink edge over here is an edge that was learned in one direction and really should have been learned in the other direction. That is, it's reversed relative to our current biological understanding. And some other edges, specifically the ones that are these dashed lines, for example, this one, or that one, were omitted from the network. That is, they should have been there but were not correctly learned. So this is definitely not perfect, but nevertheless it's a surprisingly impressive success story in the context of taking just a single data set and reconstructing many years of learned biology. What's also important is that some of these edges that were learned, these two red ones, were ones that had some very weak support from the literature. That is, they were known to exist in a different cell type than the B cells in which these data were acquired, but were not known to exist in B cells. And one of these, specifically this one, was subsequently tested in a wet lab and found to be true in B cells as well. And so the network revealed to biologists a connection that had not previously been established in the context of B cells and turned out to be of importance because it corresponds to what's called crosstalk or communication between two different biological pathways. And so this is a very nice example of how Bayesian network structure learning can be used in this different paradigm, where not only do we not necessarily have expert knowledge and we want to improve performance, but rather discovering the network structure is a goal in and of itself. To summarize, Bayesian network structure learning is a useful tool for building better predictive models when domain experts don't know the structure, and that can be useful both for making predictions about new instances, but also, as we saw in this most recent example, for knowledge discovery as well. So for these very two different purposes. We've shown that, in general, finding the highest scoring network structure outside the context of forests or trees is an NP-hard problem, and that is typically solved using simple heuristic search. And most commonly, this is done using local steps that modify the network using small local perturbations, such as edge addition, deletion, or reversal. And in order to avoid the local optima that one would get from this, we typically use not just simple hill climbing, but modify that using both taboo lists that avoid sort of undoing recent changes, as well as random restarts so as to explore different parts of the space. Well, this is a surprisingly successful strategy. It turns out that there are actually much better algorithms out there that make much larger changes in the space simultaneously. These are computationally more expensive, are harder to implement, but can make much larger moves in the space, and therefore, especially for large spaces where the signal isn't immediately clear, can find better structures than a simple greedy search. We talked about how the problem of learning a general Bayes-net structure can be viewed as a combinatorial optimization problem in which we are trying to find a high-scoring network structure, and how that problem is usually solved by some kind of heuristic search over the space of Bayes-net structures. Let's talk now about the computational cost of this algorithm and how we can use the property of decomposability, which we also previously used in the context of tree learning, to considerably reduce the computational cost of this algorithm. So as a reminder, the heuristic search procedure that we discussed iteratively moves over the space of networks. And so if this is the network that we're currently at, we need to evaluate several different moves away from that network that perturb it, usually in local ways, by adding, deleting, or reversing an arc. We then score each of these subsequent networks and see which of those has the highest score and take that move. And one can also have other algorithms that evaluate, that don't necessarily make the greedy move at each point, but the basic idea is the same. So what is the computational cost of this algorithm? Let's do the naive computational analysis, what we would get if we were to do the naive implementation of this. So how many operators are there in each search step that we need to evaluate? So in a Bayesian network with n nodes, we have n times n minus 1 different possible edges. Now, each of those edges is either present in the graph or not present in the graph. If the edge is present in the graph, we can either delete it or reverse it. And if it's absent, we can add it, which means that effectively we have either 2 or 1 possibilities for each of those n times n minus 1 possible edges, and so we have O of n squared possible operators that we need to evaluate at each point in the step, each step in the algorithm. What is the cost of evaluating each of the candidate successors that we would get by taking one of these operators? So, reminding ourselves that there are multiple components in the score, one for each variable in the network because of the decomposability property. So we have n different components. And for each of those, we have to look at the sufficient statistics and compute the resulting entry in the score corresponding to that variable. Computing sufficient statistics requires a traversal over the training data, and so that's something that takes O of m time, where m is the number of training instances. So altogether, this step requires O of n times m. Now, we haven't talked about this, but one also needs to make sure that the resulting graph from this operator is in fact acyclic, and so we need to do an acyclicity check. This is something that in general requires O of little m time, where m is the number of edges in the graph. So altogether, if we sum up all of these different pieces of the cost, we end up with computational cost, which is O of n squared times mn plus little m, where by and large little m is usually dwarfed by big M times n. And that is the cost per search step. Now, if you think of a network that's not even necessarily that large, something that has 50 or 100 variables, so that n is 50 to 100, and the number of training instances is 10,000, this can get really, really large and generally intractable to do in a lot of situations. So how can we improve on this? Let's see how we can exploit the decomposability property to get a significant computational savings in the search process. Let's first look at a single small operator, such as the one where we add an edge between B and D to this network where such an edge did not exist before. And let's consider the score that we had for the original network, which in this case is because of the decomposability property, is the sum of family scores for the individual variables. So we have a component that lists the score of A relative to its empty set of parents, the score of B relative to the empty set, C relative to its parents A and B, and D relative to its parent C. Let's compare that to the score of the network following the move. And we can see that this score for the new network is actually very similar to the score of the original network, because for the same decomposability property, we can break up the score into these little components, and since most families haven't changed, that component in the score is going to be the same. Specifically, we're going to have the exact same score for A relative to its empty parent set, the same score for B, the same score for C, and only this last score for D is now going to be different because of the fact that we've modified the family for D. But that immediately suggests that we don't really need to recompute these earlier components of the score because they haven't changed. We only need to compute the last component corresponding to D. In fact, we can do better than that by, instead of considering the absolute score, instead we're going to compute what's called the delta score, which is the difference between the score of the network following the change, this network, and the score of the original network. And we're going to compute the difference between those two scores, which, as we can see, is just the difference between the scores of the two families for D, the BC family in the new network versus the C family in the original network. And that delta score is going to be something that we can compute just looking at a single family, ignoring the rest of the network. The same thing happens for other local operators. So for example, if we consider now the deletion operator that deletes an edge between B and C, and we look at the delta score, that delta score only cares about the family C because that's the only family to have changed, and that's going to be, again, the difference between the score of C with a single edge A minus the score of C with the family AB. So again, only one family gets affected by this change. For an edge reversal, the situation is a little bit more complicated because we can see that by flipping the edge from B to C and making it go from C to B, there's actually two families that are affected, the B family and the C family. But that's still just two as opposed to the entire network. And so we can see that that delta score is going to have two components. One is the delta score for the C family, and the second is the delta score for the B family. But in either case, we only end up affecting either one family in the case of edge addition or in the case of edge deletion, or at most two families in the case of edge reversal. And so that means that we only have to consider a much smaller fraction of the network when computing the delta score. A second use of the decomposability property comes up when we consider multiple consecutive steps of the search algorithm. So let's imagine that in the previous step we decided to take that step that added the edge from B to C, and now we have to consider the next step in the search. Well, what are the operators that are conceivable in this next step of the search? For example, one such operator is to delete the edge from B to C. This one. And notice that that edge deletion operation is in fact an operator that we also considered in the previous step of the search before we decided to add the edge from B to D. Now, not only is this operator the same, notice that the family of C hasn't changed between those between those two cases. In both of these cases, when we're considering the move, C has the parent set A and B. And so the delta score for that particular move is not going to change either. Specifically, if in this case, the delta score was the score of C given family A minus the score of C given the family AB, we have exactly that same score, the same delta score in the previous step. That is, these two delta scores in the previous step and the new step are exactly the same, and so there's really no point to recompute it. So which scores do we need to recompute? The only scores that we need to recompute are the ones that were affected by the step that we just took. So specifically, if we took a step that modified the family of D, then any step that involves an additional change to the family of D will have a different delta score because the family is now different in doing the comparison. However, families that were not affected by the move don't need to be recomputed. So to summarize, we only need to rescore delta scores for families that changed in the last move. So let's summarize the computational cost of this procedure. What's the cost per move? Having decided to take a move, we have only one or two families that were affected by that move. That means that only O of n delta scores need to be computed because for a given family there's only n possible edges that impinge on that family. So only O of n delta scores need to be computed, and for each of those we need to compute sufficient statistics, which takes O of m time. So altogether we have O of little n times m as the cost of doing this step, which is actually 2 orders of magnitude better than the O of n cubed times m that we had for the original naive computation. Now this tells us the cost after we pick a move. What about the cost of picking the move? Now, naively, we might say that there's n squared possible operators that we can consider in any given move, and so we need to evaluate each of them and pick the best one, or consider each of them and pick the best one. But in fact, we can do considerably better by the use of clever data structures. Specifically, we can maintain a priority queue of operators sorted by their delta scores. Now, when we rescore those O of n operators, in this step over here, we need to modify the score of those operators and reinsert them into the priority queue in their appropriate place. But that's a computation that requires O of n log n time because there's only n of them. And once we have done that, the best operator will be at the top of the list, which we can then identify and take in constant time. And so this priority queue saves us complexity by taking us from O of n squared time for picking this, for traversing the set of operators to something that requires O of n log n. And so altogether, we've actually saved a considerable cost in both of these steps. It turns out that one can get an even higher level of computational efficiency based on a different observation. So it's a fact that in most network learning algorithms, the plausible families, the ones that have some chance of being selected, are variations on a theme. That is, for a given variable A, there might be some number of variables, B1, B2, up to bk for a very small k that are reasonable parents to be selected as parents for A. And so how do we exploit that property in to get computational savings? Turns out there's two different ways that one can utilize this. The first is the fact that because we have the same set of variables being constantly considered as being candidate families, it means that we can use sufficient statistics that we computed in one step and reuse them in a different step if we cache them, because we're likely to encounter the same family more than once. We might encounter B as a parent of A and A as a possible parent for B, and for both of these we have the sufficient statistics AB that are going to be utilized for both of them. And so if we compute this once and then cache it, these sufficient statistics, we don't have to recompute them again. That turns out to make a huge difference in terms of the computational cost of this algorithm. The second way in which this could be used is that if we can identify in advance the set of B1 up to Bk that are reasonable parents to consider for A, we can restrict in advance that set and not consider other parents at all, which reduces our complexity from O of n to O of k, where k is some bound on the number of plausible parents that we're willing to consider. Now this is a heuristic in the sense that this is a restriction that could actually change the outcome of our algorithm. It's not just a way of reducing the cost, but it turns out to be a very good approximation in practice. To summarize, it turns out that even the fairly simple heuristic structure search that we employ in such as greedy hill climbing can get expensive when n is large, because the naive implementation has a cubic dependence on n. But we can exploit the decomposability property that we also exploited in the context of tree learning to get several orders of magnitude reduction in the cost of this search. We can also exploit the recurrence of plausible families at multiple steps in the search algorithm to get further computational savings and also restrict the search space to get better computational properties. N times n minus 1 different. So in a Bayesian network with n nodes, we have n times n minus 1 different possible edges. Now, each of those edges is either present in the graph or not present in the graph. If the edge is present in the graph, we can either delete it or reverse it. And if it's absent, we can add it, which means that effectively we have either 2 or 1 possibilities for each of those n times n minus 1 possible edges, and so we have O of n squared possible operators that we need to evaluate at each point in the step, each step in the algorithm. What is the cost of evaluating each of the candidate successors that we would get by taking one of these operators?